Hello everyone, welcome to yet another video of Measure Theory course Non-Measurable Set. First of all, for introducing non-measurable set, we want to define some other term used here. Definition: If x and y, are real number in 0 to 1. Okay, this is a closed interval from 0 and open interval from 1. Okay, the sum modulo, the sum modulo 1, the sum modulo 1 denoted by plus dot of x and y is defined by here we are defining sum modulo 1. Okay, if x and y are real number which belongs to closed interval 0 to 1 open interval, the sum modulo 1 uh, plus dot if x and y is defined by x plus dot y equal to, it is x plus y when x plus y is less than 1, and it is x plus y minus 1 when x plus y is greater than equal to 1. Okay, let's take some example. Let x 1 by 3 plus dot 1 by 4. Then we know that 1 by 3 plus 1 by 4, sum of 1 by 3 and 1 by 4 is 12 LCM, 3 4 ja, 4 3 ja, 7 by 12, which is less than 1. Okay, then this formula will be applied. Okay, and here it will be 1 by 3 plus 1 by 4, and answer is 7 by 12 because x plus y 1 by 3 plus 1 by 4 is less than 1. Okay, and let 2 by 3 plus dot 1 by 2, then we can write it 2 by 3 plus 1 by 2, and first we get the sum 3 2 just 6, 2 2 just 4, 2 3 just 6, 3, it is 7 by 6. 7 by 6 is greater than 1, then we have to apply x plus y minus 1. Okay, then it is 7 by 6 minus 1 remain 1 by 6. Now you understand the definition of uh, the sum modulo plus dot. Okay, now we take another definition. Definition: if E is a subset of 0 to 1. Okay, this close interval from 0 and 1, open interval from 1, then the translate modulo 1 of E, translate modulo 1 of E by y is defined to be the set given by E plus dot y equal to z, and such that z equal to x plus dot y, where x belongs to E. Okay, here we can see if E is a subset of 0 to 1, E here given E is subset of 0 to 1, then the translate modulo 1 of E, then translate modulo by y is defined by the set. We can define translate modulo as E plus dot y equal to z, and such that z equal to x plus dot y, where x belongs to E. Okay, x belongs to E. We can see here if x and y belongs to 0 to 1, it is open interval, then x plus dot y always belongs to 0 to 1. Here we can see if x and y is belongs to 0 to close interval 0 to open interval 1, then x plus dot y always belongs to close interval 0 and open interval 1. We can check, we can take example, because we know that the value of x and y is less than 1. So we have taken value, uh, it is an example. Let x taken zero point 0.9 and y taken 0.8. Okay, then x plus dot y, we know that we have two formula for this. X plus y, when x plus y is less than 1, and x plus y minus 1 when x plus y is greater than equal to 1. Okay, when x is zero point 0.9 and y is zero point 0.8, then it is 1.7. 1.7 is greater than 1, then answer will be 1.7 minus 1, answer will be 0.7. So it is given when x and y belongs to close interval 0 to 1, then x plus dot y always belongs to 0 to 1. Okay, we can see here this, by this example we can verify this property. Okay, and second property is the operation plus dot is commutative and associative. This is another important property. The operation plus dot is commutative as well as associative. We know that commutative is a plus b equal to b plus a. Okay, in addition perspective, and associative is a plus b plus c equal to a plus b plus c. Okay, here this is given. The operation plus dot is commutative and associative. Okay, now we start a theorem, very important theorem of non-measurable set, which is very important for your examination purpose also. So let's start that theorem. Theorem is, okay, let each subset of 0 to 1 be a measurable set, and y belongs to 0 to 1 be given, then the set e plus dot y is measurable, and measure of e plus dot y equal to measure of e. Okay, this is very important theorem. If E subset of 0 to 1, 1 is open interval, be a measurable set, है, E is a measurable set, and Y which belongs to 0 to 1, 1 is open here, be given, then the set E plus dot Y is measurable. E plus dot Y is also measurable, and we can write measure of E plus dot Y equal to measure of E. Okay. For this, define we assume E1 equal to, we have taken E1 E, E intersection 0 to 1 minus y, and here from 1 minus y it is open interval. It means E1 is intersection of E and interval, close interval 0 and open interval 1 minus y. Okay, and E2 we have taken E intersection, here it is 1 minus y and 1 open interval 1. Okay, clearly E1 and E2 are two disjoint measurable set. Okay, we have taken E1 and E2 to disjoint. Disjoint. Why these two sets are disjoint? Because we can see E1 is intersection of E and 0 to 1 minus y. Okay. So we know that E is subset of 0 to 1 and 0 to 1 and 0 to 1 minus y. Okay. We can see 0 to 1 minus y, and E2 is E intersection 1 minus y and 1. Here we can see 1 minus y and 1. Here we can see 0 to 1 minus 1. So we can see there is no common any common interval in between E1 and E2, and clearly E1 and E2 are disjoint measurable set. Okay. EB, E is given measurable and intersection of two measurable set is also measurable. We know that the important property intersection of two measurable set is also measurable. Also, we can write here, let's also we take E1 union E2. We have written E1 as E1 intersection close interval 0 and open interval 1 minus y. Okay. And union E2 is uh, E intersection, sorry, it is E. Okay. E intersection 1 minus y open interval 1. Okay. This is we can apply here formula. Uh, you can easily understand this if you have previous knowledge of set theory and set operation is in your mind. Okay. If set theory is not very good, then there is some problem for you, but you can still understand very easily if you look it very carefully. Here E intersection close interval 0 to 1 minus y union E intersection 1 minus 1 y close interval and 1, we can write it as E intersection here 0 to 1 minus y union 1 minus y to 1. This is very easy concept in set theory. Okay. E intersection close interval 0 to 1 minus y union E intersection 1 minus y close interval to 1 open interval. We can write it as E intersection 0 to 1 minus y union 1 minus y to 1. Here we can write E intersection and union of 0 close interval 1 to 1 minus y open interval union 1 minus y close interval and 1. We can easily understand the union of this is 0 to 1. Okay. And we know that we assume it is given to us that what is given is subset of 0 to 1. Okay. It is also here is open interval. Okay. 0 to 1. It is open interval. Then we can write it as E. Okay. This is simply we can write E. Now takes another step. We know that E equal to E1 union E2, which I prove here. E1 union E2 equal to E. Now measure of E equal to will be measure of E1 plus measure of E2. Okay. Now we will see now E1 plus dot y equal to what we have studied, x plus dot y such that x belongs to even, which I have uh, definition of translate modulo even plus dot y equal to x plus dot y if such that x belongs to even. Okay, and here we know that x plus dot y such that, and even we can see from here, you can see here we can write it as x less than 1 minus y, because even equal to e intersection 0 to 1 minus y. Okay, we can write it as then plus y less than 1 and x belongs to even. Okay, but we know that uh, uh, as definition of sum modulo 1, x plus dot y, x plus dot y, and when x plus y is less than 1 equal to x plus y, when x plus y is less than 1. Okay, okay, it is x plus y such that x belongs to even. We can write it as even plus y. Okay, then first part we get here m dot, what is first part? First part is measure of m e plus dot y equal to measure even, what we get, measure of even plus y, and it is equal to mv1 even translation invariant property. Okay, property. We proved m even plus dot y equal to measure of even plus y, and we know that measure of even plus y equal to measure of even, as even plus y is measurable, even plus dot y is also measurable, and we can take m1 even plus dot y equal to measure of even plus y equal to measure of even. Now we take similarly for the this for measure of e2 plus y. Okay, similar process we start for e2. Similarly, e2 plus dot y equal to, we know that z plus dot y such that z belongs to e2. Okay, now z plus dot y such that z belongs to e2 implies z, we know that z is greater than equal to belongs to e intersection uh, close interval 1 minus y and open interval 1. Okay, so z greater than 1. Okay, what we can see, e intersection close interval 1 minus y and 1. Okay, e2. Then we can write it as z plus dot y, and we can write it as z plus y greater than equal to 1 and z belongs to e2. Here we know that z plus y is greater than equal to 1. We know according to when x plus y, x plus, when x plus y is greater than equal to 1, then it is x plus y minus 1. Okay, okay, we know the formula. When x plus y is greater than equal to 1, we have studied in some modulo 1 definition. When x plus y is greater than equal to 1, then x plus dot y equal to x plus y minus 1. So we can see from here it is greater than equal to 1, then we can write it z plus y minus 1, where z belongs to E2. Okay, and we know that z belongs to E2. We can write it as E2 plus y minus 1. Similarly, we can E2 we E2 E2 plus dot y is measurable, and we can write m E2 plus dot y equal to m of E2 plus y minus 1 equal to measure of E2. Okay. By using both this equation, we can easily conclude the result. We can see E1 E1 plus dot y equal to E1 plus y, and E2 plus dot y equal to E2 plus y minus 1, which I have proved. And so E1 plus dot y and E2 plus dot y are disjoint, measurable sets. With these two results, we have proved m E1 plus y equal to measure of E1, and second result, measure of E2 plus dot y equal to measure of E2 plus y minus 1 equal to measure of E2. Okay, these two results we have proved. Since M is translation invariant, we know that measure is translation invariant. We can write it as E plus dot y. We can write it as E is E1 union E2 plus dot y. Now we can write it as E1 plus dot y union E2 plus dot y. Okay. Hence, E plus dot y is a measurable set with measure of E plus dot y equal to measure of E1 plus dot y plus measure of E2 plus dot y. Okay, and here we can write it is, we have proved earlier in earlier step, then measure of E1 plus dot y equal to measure of E1, and measure of E2 plus dot y equal to measure of E2, and we know that measure of E1 plus measure of E2 equal to measure of E. Okay, measure of E. So here we can see in M E plus dot y equal to measure of E, which is required proof we want to prove, because theorem is let E subset of 0 to 0 close interval 1 to open interval be a measurable set, and y belongs to close interval 0 to 1 open interval given, then for set E plus dot y is measurable and M E plus dot y equal to measure of E. I hope you understand this video. This is very important for you for uh, measure theory syllabus. Okay, this is so thank you very much, and if you like this video, subscribe this channel, share to your friends also. Okay, thank you.